Back in 2002, during routine oil and gas exploration, two geoscientists from BP were combing through seismic data from the southern North Sea. Their work was supposed to be about identifying subsurface structures for hydrocarbon exploration, but they noticed something odd in the seismic images. There appeared to be concentric rings beneath the seabed, patterns that didn't fit neatly into the normal geological story of the region. When they looked closer, they thought it resembled something that might form from an asteroid impact, rather than ordinary sedimentary or tectonic processes. They published their observations in Nature in 2002, and with that, the Silver Pit mystery began. Several alternative theories were floated after 2002, including the idea that the site was nothing more than a collapsing salt dome rather than an asteroid crater. But it wasn't until this year that scientists finally got to the bottom of the mystery. At last, a site's true origin has been revealed. It is without a doubt an impact crater. The Silver Pit structure lies about 130 kilometers east of the Humber estuary, roughly 80 miles off the Yorkshire coast, buried deep beneath the floor of the North Sea. At the surface today, the water there is shallow by ocean standards, about 40 meters or so. Beneath that lies hundreds of meters of sediment that had built up since the impact. When it happened, sea levels were different, but the site was still underwater. At the time of the impact, the asteroid would have smashed into a seabed covered by perhaps a few hundred meters of water. The geology of the region includes Upper Cretaceous chalk, Jurassic shells, and even deeper Perrine salt deposits. These layers played a role both in how the crater formed and how it was later preserved. The crater itself is about 3.2 kilometers in diameter at its core, but a disturbed zone spreads outward as much as 18 to 20 kilometers. At the center sits a raised bump, the so-called central uplift dome, which is typical of larger impact craters that undergo collapse and rebound after the initial explosion. Around the central peak are concentric rings and faults, structural features that ripple outward and show up clearly in seismic images. Taken together, the shape and the geometry strongly resemble other confirmed impact craters around the world. As mentioned before, from the moment it was first described, geologists argued over whether Silver Pit really was an impact crater. An alternative explanation was salt tectonics. Beneath the area lie thick layers of Perrine salt which are known to move and deform under pressure. As salt migrates or dissolves, overlying sediments can collapse, creating circular features that sometimes mimic impact structures. Many geologists in the years after 2002 believed Silver Pit might be one of dozens of such salt-related collapse structures in the North Sea. The problem for the impact theory was that while the structure looked like an impact crater, it lacked classic smoking guns such as shocked quartz, melt rocks, or ejector deposits. In fact, in 2009, a formal debate at the Geological Society of London concluded with most geologists leaning toward a non-impact origin. For more than a decade, Silver Pit's true story remained unsettled. What changed recently is that new data have finally provided the missing piece. A team revisited the site with improved three-dimensional seismic imaging and also analyzed mineral samples more closely. The higher resolution data showed the crater bowl, the central peak, and concentric faults in clearer detail than ever before. More importantly, the team identified microscopic mineral grains displaying shock deformation, evidence of pressures far beyond what normal tectonics can achieve. Shock metamorphism is widely considered the gold standard for proving an impact origin. In addition, fossil assemblages in sediments above and below the crater allowed scientists to refine the timing, showing that the event happened around 43 to 46 million years ago in the Eocene epoch. Numerical models of impact dynamics confirm that the size and shape of Silver Pit could indeed be produced by an asteroid of about 120 to 160 meters, striking at typical cosmic velocities of 20 to 50 km/s. If you imagine the scene 43 million years ago, a rocky asteroid perhaps 150 meters across plunged into the North Sea basin, traveling at tens of kilometers per second. It had the kinetic energy of hundreds of megatons of TNT. When it hit, the water column briefly cushioned the blow, but was instantly vaporized along with much of the rock beneath. The impact gouged out a bowl 3 kilometers wide, blasted apart chalk and shale layers, and caused the seabed to rebound into a central peak. Rock fragments and water were thrown skyward while enormous shock waves radiated through the basin. In the sea above, waves as high as a few hundred meters would have formed, sending megatsunamis outward that could have battered coastlines around northern Europe. For marine life nearby, the event would have been devastating, but on a global scale it was not large enough to trigger mass extinctions like the far bigger Chicxulub impact that ended the age of the dinosaurs. One of the reasons the crater has survived so well is that it was quickly buried under layers of sediment. Over millions of years, additional strata sealed it away from erosion and surface weathering, preserving its shape like a fossilized scar. Being offshore also helped. Impact craters on land are often eroded, faulted, or buried by subsequent volcanism. But under the seabed, the structure remained intact until seismic surveys for oil and gas exploration revealed it. The advances in imaging technology combined with new stratigraphic dating methods and microscopic mineral analysis finally gave geologists the tools they needed to settle the argument. What makes the Silver Pit story even cooler is how it all came together by chance. Oil companies were just out there scanning the seabed looking for the next big gas reservoir, and they accidentally stumbled on one of the best preserved asteroid craters in Europe. They went trying to rewrite Earth's history, but that's exactly what happened. Then came the geologists who argued back and forth for years. Was it salt collapse or was it really an impact? In the end, the evidence tipped toward the asteroid theory, and suddenly this quiet patch of the North Sea had a dramatic backstory. I like to think about it this way. A rock the size of a city block comes screaming in from space, slams into a shallow sea, and leaves a scar that survives for over 40 million years buried under mud and chalk. We only found it because of modern technology and a bit of luck. The Eocene world in which this impact occurred was warm and dynamic. Mammals were diversifying, marine ecosystems were rich, and Europe looked very different. The North Sea basin was shallower and more restricted than it is today, making the tsunami effects potentially severe in local regions. Still, it was a contained catastrophe, something that shook northern Europe, but left little trace elsewhere. If anything, Silver Pit demonstrates what happens when an asteroid of medium size, far smaller than a dinosaur killer, but large enough to devastate a region, strikes the Earth. Even with the new evidence, some questions remain. Ideally, geologists would like to recover more core samples from the crater central peak or rim to find unambiguous melt rocks. They would also like to identify tsunami deposits or ejector layers in nearby sediments that could be tied directly to the event. And while the seismic images clearly show concentric rings, researchers are still debating the precise mechanics of how those rings formed, whether by slumping of sediments into the crater or by direct fracturing from the impact shock. These lingering details are the final pieces of the puzzle. The Silver Pit discovery matters for more than just local geology. It adds to the global catalog of confirmed impact craters, which is surprisingly small given the age of the Earth. Events of this scale are rare in human timescales, but they are not impossibilities, and understanding their frequency and consequences helps inform risk assessments for the future. So, hats off to Earth's newest confirmed impact crater. Hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.